Good morning, friends. I wanted to link a video to a problem from your spiral. So this is from your spiral, and if you still have your spiral, you can go and get it and use it right now. But I wanted to link a problem that was similar to the exit ticket problem. So I'm going to model how I would finish this problem out, and then I want you to take notes, upload a picture of your notes, and then use these notes to help you answer the exit ticket problem. Okay? So lesson 7 up here at the top. Let's start by explaining what's happening here. So what's happening here is that there is a family. They can either each night play a board game, and that's represented with a B, or they can play a card game, and that's represented with a C in our tree diagram. The way that they decide each night whether or not they play a board game or a card game is they roll a tetrahedral dice, which means the dice has 4 sides. Now, looking back at this problem, it says, for this family, a card game will be played if the die lands showing the value of 1. So that means on the dice, it lands showing a value of 1. The family is then going to play a card game. And the family plays a board game if they roll the dice and it shows a 2, a 3, or a 4. Okay? So that makes the probability of the board game be, on any given night, 75 hundredths. So let's think about why the probability of it playing a board game is 75 hundredths. So if we think about this dice, there are 4 different sides, 4 different numbers that could show up 4 different outcomes. Well, the probability of the outcome being a 1, the probability of it being an outcome of it landing on a 1 is 1 out of 4. It can land on a 1 out of 4 times. Probability of it landing on a 1 out of 4. So that means the probability of us rolling a 1 is 0.25, or the probability of the family playing a card game is 0.25. So now let's think about what the probability of us rolling any other number would be, a 2, a 3, or a 4. So I could have 2, a 3, or 4. That's 3 different, the probability of it being a 2, a 3, or a 4. That's 3 out of the 4 outcomes. 3 out of the 4 outcomes, which is equal to 75 hundredths. 75 hundredths. So, if this is true, then that means I should be able to add 75 hundredths to 25 hundredths to get a probability of 1, or certain, that no matter when I roll the dice, I will have an outcome. So, checking my probability, if I take 0.25 and I add it to 0.75, I do get 1. So the way that I have distributed my probabilities is correct. Okay, now that we understand that if we roll a 1, the family will play a card game, and if we roll a 2, a 3, or a 4, the family will play a board game, let's start constructing our tree diagram. So in our tree diagram, we see on Monday, they roll the dice. The probability of them playing a board game is 0.75. Probability of card game is 0.25. Again, on Tuesday, those probabilities stay the same. So the second event could be a board game or a card game stemming off of Monday. Second event could be a board game or a card game stemming off of Monday's outcome. Then we see another outcome of Wednesday. Wednesday, the family could play a board game or a card game. And you'll notice that the probability of board game or card game stays the same from the first event, because no matter what, if we roll a 1, we'll play a board game. If we roll a 2, 3, or 4, we will be playing a card game. And that doesn't depend on the day, okay? Doesn't depend on the day. The probability between those 2 outcomes stays the same. But now, after we get to our final outcome in the tree diagram and we are creating our sample space, we need to move on to criteria for success number 3, which is the numerical probability. We need to calculate the numerical probability of each of these outcomes. And the way that we do that is by multiplying. The way that we do that is with multiplication. So what you can see here is that this problem has already started to do that. It wants to know the probability of them playing a board game every night of the week, Monday, Tuesday, and Wednesday. So we're multiplying the probability of it being a board game on Monday, 0.75, times the probability of it being a board game on Tuesday, which is 0.75, 0.75. And then multiplying it by the probability of it being a board game on Wednesday, which is 0.75. So when we multiply those three factors, we get an answer of 42 hundredths, or the probability of it being a board game 3 nights in a week is 42 hundredths. So moving on to the second sample space, board game is 0.75. I'm multiplying it by the board game probability, which is 0.75. And then on the third night, I would need to multiply it by 0.25 to represent the probability of it being a card game. When I use my calculator to do this multiplication, I get 0.14. Okay, now looking at the third outcome, I have BCB, board game, card game, board game. I noticed that I have the same number of B's in this outcome as I do in this outcome. And I have the same number of C's in this outcome as I do in the previous outcome. So that means that these probabilities are the same. It's the same probability as the previous example. So, or the previous outcome. I can just write that down, 0.14 right away. Okay, the fourth outcome. I'm taking B, or 0.75, times it being a card game, which is 0.25, times 0.25. And when I do that, the probability is 0.047. Once again, I see two B's and a C, so I can just copy down 0.14. Here I have two C's and a B, so I can just copy down 0.047. And here I have three C's, so I'm going to multiply 0.25 to the third power, or 3 times, to get 0.016. So now I actually have all of the probabilities of each of my outcomes. Now I have all of the probabilities of each of my outcomes. And when I pay special close attention, you'll notice that the distribution of probability between B and C stays the same as we increase events. So you'll notice probability of C here is 0.25, probability of B here is 0.75. Moving on to the second event, probability is still for B 0.75 and probability for C is still 0.25. Moving on to the third event, the probability of B is still 0.75 and the probability for C is still 0.25 in the third event. So those are the values you're using to multiply. Then I changed the problem at the bottom to better match a problem like on your exit ticket. I'm going to read it right now. It says, what is the probability of the family will have at least one night of card games? At least one night of card games. So I'm going to look at my sample space and see where I see at least one C, or at least one C. So that means I can have one C, I can have two C's, or I can have three C's. None in this first one. There is a probability of a card game in the second one. So I'm going to have 0.14. And then I need to add that to the probability of the second event, which is 0.14. And then I'm going to add this outcome right here, the probability of this outcome, which is 0.047, plus the probability of this outcome, which is 0.14, plus the probability of this outcome, which is 0.047, plus the probability of this outcome because it is 0.047. And then finally I need to add the probability of this final outcome, which is 0.016, because all of those outcomes contain at least one card game. When I add that together, the probability of at least one night being card games for this week would be 0.578. 578 thousandths. Make sure you have copied down all of these notes. You can grab your spiral if you would need to. Make sure you read the exit ticket carefully. I will check your answers before you post if you would like me to. Just text me or call me. And you can redo this assignment if you need to, if you don't like your score. Please remember to use the criteria for success as you're solving. And have a great weekend. Happy Friday.